In number 23, we want to write an expression for the slopes of the secant lines. So in this diagram, instead of using a and b, we're using c and x for the x values. All right, so the slope, I'll write m is equal to, and we have f of x minus f of c for the difference in the y values, and x minus c for the difference in the x values. All right, after all, this point is c f of c, and this point is x f of x. So again, looking at the slope formula, here are the difference in the y's in the numerator and the difference of the x's in the denominator. In 23b, again, we want to write down the slope of this secant line that we see here. This time we're labeling the x values as x and x plus h. All right, so this point is x comma f of x, and this point over here is x plus h comma f of x plus h. So let's write down the slope using this notation. Change of y, f of x plus h minus f of x, and change of x is x plus h minus x, and that simplifies to just h. So that's another way of expressing the slope of the secant line. All right, 24 is an easy question. We want to write down the limit definition of the derivative, so let's just write that down. F prime of x is equal to limit h goes to 0, f of x plus h minus f of x over h. In 25, we want to use the limit definition to find f prime of 2, where f of x is x squared plus 5. Okay, so we're going to, again, write down that limit definition here. We have it over here. Let's look at that again. But we'll substitute in x equal 2. Okay, so writing that down, we have f prime of 2 is equal to limit h goes to 0, f of 2 plus h minus f of 2 over h. That's equal to the limit h goes to 0. All right, we're substituting in 2 plus h right here into this function. So that would be 2 plus h squared plus 5 minus f of 2, substitute into here, minus 4 plus 5. 2 squared plus 5, that's just 9 over h. All right, so this is 9. Let's square out 2 plus h squared. That would be 4 plus 4h plus h squared plus 5 minus 9 over h. So notice here 4 plus 5, we have 9 minus 9, so all of these are equal to 0. So here we end up with limit h goes to 0. 4h plus h squared over h. Divide top and bottom by h. That's always the second to last step. And here we get 4 plus h. And now we're ready to take the limit, and we get 4. H went to 0, and we get 4. In part B, we want the equation of the tangent line to f of x at x squared the equation of the tangent line to f of x equal x squared plus 5 at x equal 2. So let's just remember what we found in part A. We found that f prime of 2 is equal to 4. So let's write that down. So that's going to be the slope of the tangent line. At x equal 2. So if we use the formula y equal mx plus b for the equation of a line, we have y is equal to 4x plus b. And we have to figure out what b is. We'll substitute in a point on the tangent line, which is going to be the point where the tangent line touches the curve. So we use that x value, x equal 2, and to find the y value, substitute in here. So the point on the line is x equal 2, and y is f of 2. So let's figure that out too. F of 2, that's 4 plus 5, that's 9. 2 9's our point. Let's substitute that in. X, y. 2 for x, 9 for y. And that way we'll figure out what b is. Okay, so we have 9 is equal to 8 plus b. So b is 1. And continuing here where we left off, y is equal to 4x plus 1. Now we want to use the definition of the derivative to find f prime of x for f of x equal x squared minus 2x plus 3. All right, I want to find f of x plus h first. Just substituting into there. Okay, opening parentheses, x squared plus 2hx plus h squared, opening parentheses here, minus 2x minus 2h plus 3. Okay, and now let's look at the limit definition. Okay, so we have f prime of x equal limit h goes to 0 okay, we just wrote out what f of x plus h is right here, all this. We're going to put all that here. And now subtract f of x we have right there. The parentheses are important because this negative applies to the entire x squared minus 2x plus 3. All right, let's open parentheses now. Okay, opening parentheses, minus x squared. Minus minus would be plus 2x minus 3. Now cancel what we can. Let's see, we have x squared minus x squared. Let's cross that out. We have minus 2x plus 2x. Cross that out. Plus 3 minus 3. Cross that out. We are left with 2hx plus h squared plus minus 2h. Notice everything in the numerator contains a factor h, so we're going to divide top and bottom by h. So we have, starting with 2x plus h minus 2. Now we got rid of h from the denominator, we're ready to take the limit. This goes to 0, and we're left with 2x minus 2. So that's f prime of x, the derivative. In part B, we want to find the point on f of x where the tangent line is horizontal. Okay, so that means tangent line horizontal tangent line has slope 0, or that's the same thing as derivative is equal to 0. Here's our derivative. F prime of x is equal to 2x minus 2. And we're just going to set that equal to 0 and solve. All right, add 2 to both sides and divide by 2. So x equal 1, that is where the tangent line is horizontal. Now that's the x value. Let's get the y value. Sub into the original function for the y value. So we have f of 1 is equal to, we're substituting into f of x, 1 squared minus 2 times 1 plus 3. 1 minus 2 plus 3, that's 2. Okay, so that's the y value. So the point is 1 comma 2. Now we want to use the alternate definition of the derivative, which is written out here, f prime of c equal limit x goes to c, f of x minus f of c over x minus c. This is the alternate definition of the derivative. To find f prime of 4. Now for the alternate definition of the derivative, we can only find the derivative at a point, at a particular x value. Like here, the x value is x equal 4. We don't use it to find f prime of x. Okay, where in this case f of x is 1 over the square root of x. So we have f prime of 4 is equal to the limit as x goes to, in this case, c is 4, as x goes to 4, of f of x, that's 1 over square root of x, minus f of c, that's f of 4. Substituting in 4 here, 1 over the square root of 4 is 1/2 over x minus 4. Now we can't substitute 4 into this point because of the 0 in the denominator. We're going to do that usual trick, multiply top and bottom by the conjugate. And hopefully we'll be able to cancel x minus 4 after we do this manipulation. In the numerator, 1 over root x, 1 over root x, that's 1 over x. Now the outer and inner cancel. And minus 1/2 times plus 1/2 is negative 1/4. Alright, the x minus 4 did not pop out. We have the difference of two fractions, but one other manipulation and we'll get where we want to be. We're going to combine those fractions in the numerator. Common denominator is x times 4, or 4x. Here we're multiplying top and bottom by 4. So we have 4 in the numerator. Here we're multiplying top and bottom by x. So we have x in the numerator. Now there's the x minus 4. And there's a 4 minus x. We can cancel these and we're left with minus 1. So finally we have the limit as x goes to 4 of minus 1 over 4x. Now we're able to substitute in 4 for x. So just go ahead and do that and we get minus 1 over 16. And that's f prime of 4. The derivative at x equal 4. Here we're using the alternate form of the definition of the derivative to show that f prime of 2 does not exist. For this f of x is x minus 2 to the 2/3. So let's try to find f prime of 2 and see why we can't do that. Okay, so we're using the alternate form of the derivative, so that would be the limit as x goes to 2, f of x minus f of 2 of x minus 2. Okay, let's just substitute in what we have here. Limit x goes to 2. F of x, x minus 2 to the 2/3. Minus f of 2. Substituting in 2 here, we get 2 minus 2, that's 0. Let's just rewrite this without the 0. And let's reduce this. We can subtract 2/3 minus 1. And we have the limit as x goes to 2 of x minus 2 to the minus 1/3. We're just putting that in the denominator. We have 1 over x minus 2 to the 1/3. So you see that the denominator is going to 0. And, oops, 1/3, sorry. The denominator is going to 0. So this is going to either infinity or minus infinity, because the x minus 2 is not going to cancel with something in the numerator. All right, so this goes to infinity or minus infinity. So this limit does not exist. Okay, and that is why f prime of 2 does not exist. In number 29, we're asked to find a function that is continuous at x equals 0 but not differentiable at x equals 0. A typical example is y equal absolute value of x, which comes to a point at x equals 0. The derivative here doesn't exist. The slope on the right is 1, because on the right we have a piece of y equal x, the line y equal x. The slope on the left is minus 1, because this is a piece of the line y equal minus x. So as 0, the slope doesn't exist. In the number 30, we have 3 curves, and the derivative doesn't exist at x equal 2 for all 3. In the first picture, we have a curve that comes to a point. All right, so we're supposed to assume here that the derivative doesn't exist because of that point. When the derivative exists, the curve is smooth. So here the answer is no, and it's because of the point. In B, the derivative also doesn't exist because here there is a tangent line at x equal 2, but it's vertical. A vertical line has infinite slope. So here the derivative would tend to infinity. So again, no, because of that vertical line or infinite slope. And here at C, this curve isn't continuous, so no. If something is differentiable, we saw it's definitely continuous. So no, not continuous at x equals C.